Welcome to the lab studio for the PLC professor. My subject today is going to be the graphical user interface with Connected Components Workbench and the Micro800. The reason that this subject is of interest is because it is different than RS Logix, both 500 and 5000. And that is, there are three columns in the variable databases that you did not see in the other software: logical value, physical value, and lock. Logical value is the value that the logic sees. Physical value is either the state of the screw terminal or the state that the controller last saw of the screw terminals when it did its last I/O scan. So as long as the controller is scanning the I/O, reading inputs, then the physical value matches the screw terminal. And likewise for outputs, as long as the program is being scanned, the output scan is taking place, then the physical value or the screw terminal value matches the logical value, or you could say the physical value matches that of the screw terminal, as long as the program is being scanned. If it's not being scanned, then the last thing that memory heard was that the physical state of that screw is either on or off. So if you go to the program mode, it's going to hold that last state. So let's go through and demonstrate that. First, we create a project, and we named our project Logical Physical Lock. And in this ladder diagram program file, I created some logic. I have a program file here with 2 rungs of logic. They aren't actually logical statements. They are for display purposes only. I want to be able to see the state of these 8 bits in memory. 4 inputs and 4 outputs. The energized output or direct coils at the end of each rung, they're just placeholders. In other words, in order to do this, I have to have a complete rung. So the rung has to have an output type instruction. So I just throw in a direct coil and put a junk bit on it. I just called it bit 0 and bit 1. What we're wanting to see is the state of digital input 0 through 3 and digital output 0 through 3 as we play with the graphical user interface. So I'm going to shrink this down a little bit. I'm going to open up the Micro800 tab. I'm going to unpin it, and I'm going to drag it off, and I think I'll place it directly underneath of. Drag the width out just to make it look tidy, and all that I need to see is the mode and maybe connect. Now I also want global variables, so I double click on that, and now I'm going to unpin it, and I'm going to move it off and over to one side. It doesn't matter which side. I'm going to shrink it down a little bit in width, because all that I need to see is the state of physical, logical, and lock. Of course, you can't see that right now because we're not online. That's something to make note of. I'm also going to collapse this down. Now, I'm only going part way with this right now to show you what happens if you do all this before you go online. Let's turn on the simulator. Well, it's not really turn it on, but let's instantiate it, meaning let's create an instance of it, and we'll bring it down here to the bottom. And notice that I'm using the software loopback interface. I'm going to turn it on, and I'm going to download. That's what I wanted you to see. Notice when the interface goes online, all of your tedious work of placing everything just where you want it on the screen just all goes south. The moral of the story is download and get online before you set up your distribution of information. So I'm going to move this all back to where I had it. I don't really need to see all of the I/O. Notice I've got all 48 I/O points displayed. So I can collapse this down a little bit as long as I've got the first 4 bits of the inputs which match right here. I need to be able to see the first 4 outputs and the first 4 inputs. Now there's some other ways you might be able to do this, but right now what I'm really interested in, and let me move this over just a little bit and drag this over just a little bit. I can collapse down alias. What I want is logical value, physical value, and lock. I want that all displayed while we're doing this. I'm going to take and drag this back up a little bit because we don't need to see any more than those 2 rungs. Drag this back in place, and this doesn't have to be that wide. You can make it a little less wide, so you lose some of the menu up here when you do that. And then drag this back up. This is what we're after right here. We want to be able to see the terminals on our simulator. We want to be able to see the state of these instructions, and we want to see what mode we're in and be able to change the mode, and we want to be able to watch logical, physical value, and the lock column. Now the lock column is tied in with forces. If you want to force I/O or force bits, then you need to deal with the lock. Okay, let's start out by noticing that we are in the run mode. And if I click on, now we're in the run mode, okay? So watch up here, digital input 0 right here. Now, I want to point out something. I've noticed that if I have a variable highlighted, in other words, the focus of Windows is on it, it may or may not show the change in state. So let's click on input 0. Notice that it shows it's on here. It shows that instruction is true, but notice nothing happened here. Now let me click on another I/O point, and notice immediately you saw wait and then the check marks. So there is a little bit of a, if you want to call it a bug or a glitch. So one thing you don't want to do is have the variable that you want to watch selected. Now you see that these are showing an anomaly of sorts by showing wait. So pick one that you're not using and let that be the focus. Okay, so let me turn that back off. See, the check marks went away. So when I click on this, notice that the physical value and the logical value, so this is the physical value right here in the simulator, this screw terminal, 0, 0, that's the physical value. This is the logical value. Now, let's put this in the program mode. It is in the program mode, and it still shows the logical value and the physical value. Now, let me turn off the physical value. Notice that it holds on to the last physical value if you're in the program mode. And notice that the logical value is still checked. See, the logical value still shows true. It's a true if on instruction, and it's showing true. Well, it's logically true in that this bit stayed on when we went to the program mode, and when we turned off the input, this stayed. So now let's go back to the run mode and watch these 2 check marks as well as right here and right here, because remember the physical value is actually off. So let's go into the run mode, and you see that these are now unchecked. That's showing false, and that's not on. It was not on. Now let's go to the program mode again, only this time we're going with the input not on. Okay, now let's turn it on. Okay, you see that it shows that it's on here, but you don't see anything checked here, and you don't see a logical value. Now let's go to the run mode. We could go over here and check that and check that. It won't let us check that. So in the program mode, you cannot check the box for the physical value. In other words, you can't update it, you can't change it, but you can change the logical. Look up here in the rung of logic, digital input 1. Notice that that does respond. this check mark here, and I'm going to click back up here because remember, I don't want the highlight here. So changing the physical value on the simulator, which would be changing the voltage level on the screw terminal, does not influence the logical or physical value. Here's the logical value in the program mode. Now let's take the inverse of that. Let's go back. We'll turn that off. We'll go back to the run mode. And remember, the only difference between the run mode and the program mode is what the processor is doing. We're back in the run mode now. And if I try to turn on the logical value, it's going to turn right back off, simply because right now you're scanning the logic and the I/O. So it's going to overwrite anything you do. But let's turn on the screw terminal. Let's turn on the input and go to program. Okay, we're in the program mode. See, nothing changed here. Nothing changed here. Okay, that's what I want to demonstrate. When it comes to the input bits, the embedded I/O or extended I/O, plug-in I/O, it doesn't make any difference. This is how the input interface works between the screw terminal and memory. So right now, we're showing the logical value is 1. See right here in the rung? We're showing the physical value is 1, but the physical value is not really 1, but what it is doing is holding on to the last physical state when you went from run to program. If I go back to program, all this is going to change because this input is now off. The screw terminal is back to 0. Even though it shows logical value 1, physical value 1, go back to run. There you go. Okay, so that's the input behavior. Well, that was the nature of the module-defined input bits. And this particular controller is a 48 I/O, 20 out and 28 in. And it really doesn't matter which bits you are working with, they're all going to behave the same. So what we did was we worked with really just digital input 0. Now we're going to play with digital output 0. And I think you've probably drawn a conclusion already that the difference is whether or not the program is executing. If the processor is in the run mode, then it is doing I/O scan. And remember that the I/O scan for inputs is to move the state of the screw terminals to bits in memory. The output scan is to move the state of bits in memory out to screw terminals. So if you're not in the run mode, neither one of those can take place. And whatever the memory or processor was last told, that's where it sets. So if an input is on and then you go to the program mode, the last thing that bit in memory heard was that screw terminal was on. So it's going to maintain that. Now you can toggle bits in memory. So if we go up here to our graphical user interface for the global variables, you can toggle logical values. That is not toggling the output. Although if you are in the run mode, as a matter of fact, watch what happens. We're in the run mode, you can see here. Down here is output 0 on the simulator, screw terminal. If I click on the physical value for digital output 0, nothing happens. If I click on the logical value, then it goes on. We see it's on logically, and we see it's on physically. Not just because it's checked here under physical value, but because this output is on. The screw terminal, remember this is a simulator, so when the screw terminals go orange with white text, that means it's simulating a voltage at that screw terminal. Okay, so logical value is 1, physical value is 1, and we see that we actually have the light on. Now if I go to the program mode, the only thing that's going to change is that we are no longer reading the bit in memory and moving the state out to the outputs. So you see output 0 immediately went off, but notice the logical value and the physical value is still the same. And because the logical value is the same, you see in logic here it shows this is true upon instruction, and it's true, which means that bit in memory is on. And it is on because I can see it right here. But that doesn't mean that the output is on. So one thing that we're emphasizing early in this course is to understand the difference between the screw terminals and the bit and memory and the interaction between bits and memory, screw terminals, and the program scan, both input scan and output scan. Now this is showing it's logically true, but here it's showing it's not on. Here it shows physical value. The reason that it's doing that is because the last time it scanned, the physical value was on. We turned this off after we went to the program mode. Now, if I click on logical value, notice that this changes because remember, this is animated by the bits in memory, the value of bits in memory. Notice the physical value is still checked. So you cannot count on the physical value being really the physical value unless you're in the run mode. That's really the bottom line to both ends, the input and the output. So at this point, what would you expect to happen if I go to the program mode? The run mode. If I go to the run mode, the outputs, the logical value isn't on, just it shows the physical value. So the instant we do a scan, it's going to correct that. See, now the physical value is off. If I try to toggle the physical value on in the run mode, it can't because the logical value is not on. And even if it were reacting in literally a few microseconds, it would override it with a logical value because the logical value is the state of that bit in memory. And you can see right here it's off. If I toggle this on here, you see, now it shows that that bit is on. Here it shows logical value, physical value. If I lock it, I'm locking it on. So if I go toggle the logical value, see, I can't change it. See, it won't change. So the physical value now shows off, but the logical value is locked on. If you're in the program mode, you get one behavior. If you're in the run, you get the other. Right now, I am in the run mode and I have it locked off. Now, if I toggle the lock, see, now it goes on. If I toggle the lock again, now it's locked on. So whatever you want to do, unlock it, change the value, and then lock it. So right now it's locked off. So no matter what I do, I can toggle it on there and notice that the physical value goes on, but the logical value does not. So when you force something, you're forcing it against the logical value. I realize this takes a little bit to wrap your head around it. Just keep in mind, the lock is used to force a value regardless of the logic. The physical value is only correct if you're in the run mode, not if you're in the program mode. Well, alrighty then. That is the story, folks. The key takeaway when you are looking at the physical value column and the logical value column, the logical value is the value that the logic sees, and the physical value is the state of the screw terminals if you're in the run mode. If you're not in the run mode, then it will be the last state that it saw when you left the run mode and went to the program mode. And of course, the lock allows you to, you basically are saying, I'm locking the state of that I/O as it pertains to being used, and I can toggle it on, off, and lock it, but it won't respond to the logic, meaning that if you've got an output locked on, it's going to stay on no matter what the logic says. If you have an input locked on or locked off, it's just going to stay that way regardless of what the actual screw terminal does. So you could say that locking is a force, or it overrides the state of the screw terminals. If you go to the PLC Professor YouTube channel, you're going to see that we have changed it a little bit. These 3 videos right here describe the 3 courses that we have available. RSLogix 500 with Micrologics, and then there's RSLogix Studio 5000, that includes the advanced, and then Learn Connected Components Workbench. And if you scroll down, you're going to see the sections. This is RS Logix 500, Micrologix, Studio 5000, and Connected Components Workbench. These are groups of playlists that you watch in the sequence shown here, and you can learn the three platforms that Rockwell Automation Allen Bradley has. We'll call it 500, 5000, and if you want to call it Micro800, Connected Components Workbench. If you go to the PLC University website and scroll down, there you see the manuals that these lectures discuss. You have 2 for 500, 1, 2, and 3 for 5000, and you have 3 of them for Connected Components Workbench. So go here to get the manuals you need for these courses, and then go back to sections, and then just start watching these videos. Enjoy your learning experience.